Okay, now capacitance is a bit related to electric field, but it's actually a whole lot simpler and less complete and shorter too. Okay, so in the first place, what are capacitors? Now, capacitors are just some sort of electrical device that looks like this. Okay, it's a cylindrical shaped looking object that you can normally find inside your electronic gadgets like your laptop, smartphone, TV, or radio. Okay, so the purpose of your capacitor is actually to store energy or to separate charge or to smoothen a rectified alternating current. Okay, in this chapter, you will learn more about how it separates charge and store energy. But for the part where you are asked to smoothen a rectified alternating current, this is actually in the AC circuit chapter. It's another different chapter. Okay, so when you say that your capacitor store energy, how does it play a role in your electronic gadgets? It's like this. You see, sometimes when you use your electronic gadgets, there will be certain instances where your power drops suddenly. So if say your power drops suddenly, your capacitor is meant to kick in order to meet the shortfall in energy. Okay, it's meant to meet the shortfall in your power requirements. And likewise, if let's say when you're using your electronic gadgets and then somehow you need more power, the capacitors again will kick in. Okay, so it's meant to give you energy when you require it, but it cannot replace your normal cells or battery because it's only usable for short term. Okay, your capacitors, they tend to charge and discharge energy very quickly. So you can only use it for very short-term usage only. Okay. Now, when you're talking about a capacitor is typically made out of two parallel metal plates, which is separated by a layer of insulator called a dielectric. Okay. So how does your capacitor actually work is that you must first charge your capacitor with a power supply. Once it's fully charged, only then can we say that it stores energy. And then you can use it to do whatever you want. But in the first place, how does it actually store energy? How does it actually charge up? You need to look at the diagram below here. So you look at the diagram below here, the component you see here is actually your capacitor, where you see that it consists of two parallel conductive metal plates and a layer of dielectric in between. Okay, so now your capacitor is initially neutral. You want to charge it up, you want it to store energy. So what you first need to do is that you need to connect it to some sort of voltage supply. Say maybe you connect it to a cell or battery here. So from there, your capacitor will now start to charge up. But how does it actually charge up is based on this principle. Electrons tend to move from lower potential to higher potential. Okay, you may remember from your AS, conventional current flows from higher to lower potential. This is when you're talking about conventional current. Conventional current is actually flow of positive charges. So it tends to go from higher to lower potential. But when you're talking about electrons, electrons tend to flow the other way around because they are negatively charged. So it tends to flow from lower to higher potential. So right now, if you look at your diagram, if I were to tell you that this cell here or battery has a PD across it of 12 volts, I could probably imagine that this potential here and this potential here could be possibly 6 volts and negative 6 volts respectively, so that the difference between them gives me 12 volts. Okay, so from there, you now look at your capacitor. Because your capacitor was initially neutral, meaning to say it carries no charge, there's no potential whatsoever, you could say that here on the right plate, it is actually at 0 volts potential. Okay, so now you see along this line here, there's actually a difference in potential now, where this one is 0 and this one is negative 6. So there's a difference in potential by right. Charges or current should be flowing between them. So if you're talking about the flow of electrons, electron will flow from the lower potential to the higher potential. So currently what you get is maybe one electron tries to flow towards the capacitor plate. Okay, it flows towards the capacitor plate, but it cannot pass through because there's a layer of dielectric in between. There's a layer of insulator in between. So what then happens is that that electron, because it cannot pass through, it will just get deposited at the right plate here. So in the process of being deposited on the right plate, it will actually cause this plate here to acquire a negative charge. Okay, so here, if your plate acquires a negative charge, your potential here, likewise, will become more negative. So from 0 volt, right now, it could probably go up to negative 1 volts in terms of your potential after you have deposited 1 electron here. Okay, so after that, if you look at the other plate, because this plate is already negatively charged, it will tend to repel another electron away from the other plate. So right over here, another electron gets repelled away and it tries to flow towards the positive terminal. Because here, you can also kind of imagine it as this. Your potential here is also supposed to be 0 volts initially when it was neutral. So if you look at this and this, 0 is lower potential than positive 6 volts, right? So electron by right should move in this manner here. Okay, it will move in this manner here towards the positive terminal of your battery. Okay, so once your electron here is being pushed away from the left plate, this plate in itself starts to become positive because you've already lost 1 electron. This plate has lost 1 electron, so it will start to become positive. So once your left plate here loses 1 electron, it becomes positively charged, your potential would correspondingly increase. It will probably become positive 1 volt potential now. Okay, so this is what happens when you are talking about an electron that's initially pushed towards your capacitor. Okay, so in this process here, you will notice that there is now going to be a potential difference established between the two plates. Originally, it was 0 volts, 0 volts, no problem, no difference in potential. But now, once you start to push just 1 electron there, you will notice that this is negative 1 volts, this is positive 1 volt. You start to have a potential difference of 2 volts here. Okay, so this is when you're talking about 1 electron only. But even when you have considered the case of 1 electron being pushed towards the right plate and 1 electron being pushed away from the left plate, you will notice that there's again still a difference in potential along this orange line here, where it is negative 1 volt and negative 6 volts, and along this blue line here, where it's positive 1 volt and positive 6 volts. So because there's still a difference in potential here, electrons will actually still flow. Okay, so this time you have another second electron that tries to go towards the negative plate. It will move along this orange line here towards the capacitor plate. And again, because it cannot go past your capacitor, it will just get deposited on the right plate here. So once it gets deposited on the right plate here, you again will say that you have a negative charge here, but your negative charge becomes even more. It becomes even more negatively charged. So that when you're talking about your potential now, from negative 1 volt, you could probably be going to negative 2 volts potential. Okay, and then after that, if you look at the left plate, another electron gets repelled away and it tries to move along the blue colored line here towards your positive terminal. And when you lose another second electron here, this part here, the left plate, the positive charge increases. It becomes even more positive, such that here your potential will now be maybe plus 2 volts in terms of potential. So now if you again look at your potential difference between them, it is now 4 volts. Okay, so again, if you then look at your diagram, there's still a difference in potential between the right and the left part of your circuit. So electron will get continuously pushed towards one plate and then repelled from another plate. So this process will actually continue until such a point where your potentials on both sides are equal. So you can see from here just now, when you push a electron along this orange side here, the potential becomes more and more negative. So it went from 0 to -1 to -6. You can imagine that if you keep on pushing electrons, you will eventually reach -6 volt potential. And then on the right hand side here, if you imagine that you keep pushing away electrons from the left plate, causing the plate to become even more positive, eventually you reach +6 volt potential. Okay, so once you have gone to this point here, you will now notice that your potentials are actually the same. For the right hand plate here, you'll notice that the potential here and potential here are the same. There's no difference in potential, so electron can no longer flow. And at the same time, if you look at the left hand side of your diagram, because your potential here is 6 volt and potential is 6 volts, you again have no difference in potential. Electrons again can no longer flow. Okay, and what is of interest to you is this: electrons cannot flow. If you were to look at the difference in potential between these 2 points here, just like I indicated this point and this point, right? If you now look at the final potential difference between these 2 points here, it will actually be equal to 12 volts. If you compare this one and this one right now, the potential difference is actually 12 volts, equal to your supply voltage. Okay, so at this point here, this is where you will say that your capacitor is fully charged. All right, so whenever you want to charge your capacitor, it will keep pushing electrons to one plate and repel electrons off the other plate, causing the PD across it to increase. But this only continues until your PD across your plate is equal to the PD of your supply voltage. Okay, so you look at the blue statement here, it was mentioned that electrons will stop moving around the circuit when the potential difference across the plates is equal to the supply voltage. So at this point here, this is where we will say that your capacitor is fully charged. Okay, so your capacitor now stores energy. All right, and in some cases, they will also tell you your capacitor is seemingly storing charge. Okay, so more on the part where we say that your capacitor stores charge, this one you need to look at the next page. Now, if you again look at the same diagram from before, you could say that as you push your electrons towards this side, you're going to cause a resultant charge of -Q here. And then if you push off electrons on the other plate, you're going to cause a resultant charge of +Q here. So right now, you could say that one plate is storing +Q charge, while the other plate stores -Q charge. But when we ask you as a whole, if you look at the capacitor as a whole, what is the charge actually stored by the capacitor as a whole? You do not actually say that the charge stored is 2Q. The charge stored is actually just Q. Okay, the reason for that is if you were to connect your capacitor to a lamp, what you will notice here is this. This is your same capacitor from before, but this time is fully charged. So you now connect it to a lamp, which is the component below here. So since your capacitor is fully charged, there's already some charge here and there's some charge here. What will happen is this: if you just consider the flow of electrons alone, because this is negatively charged, this plate here is negatively charged, you can consider this side to be at lower potential. But on the other plate here, this one is positively charged. You can consider this to be higher potential. So electron has a tendency to go from lower to higher potential. So in your case, you start to have an electron that is starting to move out of your negative plate towards the positive plate. So in the process of doing so, it will actually flow through your lamp, causing it to light up, causing it to dissipate power. So that electron continues flowing until it comes towards your positive plate and causes the plate to discharge. Because you have a -Q charge here, you can imagine that there's a -Q charge here that's being moved in this particular direction towards this other plate. So since you already repel a total charge of negative Q here, and then that negative Q is expected to come towards this plate here at the end, since you see there's negative Q and positive Q, the plate will completely discharge, leaving you with neutral. Your plate will be neutral, okay? So when your negative Q comes out here, a total charge of negative Q comes out here, this plate will become neutral. And then if that total charge of negative Q comes towards this positive plate here, it will completely discharge off the other plate too. Okay, so of interest to you is the amount of charge that is actually flowed through your lamp. Okay, so in discharging right now, what you would have probably guessed or can see here is that the only charge that is actually flowed through your lamp here is really just charge Q, a charge of magnitude Q. So the charge that is seemingly stored by your capacitor now is actually really just Q. Okay, if you refer back to the statement that I say above here, although you see that one plate stores positive Q and the other plate stores negative Q, you do not actually say that your charge is storing, your capacitor is storing 2Q. It's actually just Q itself. Okay, so this one just bear in mind. All right. Now, when you're talking about the charging and discharging of capacitors, this often take place in a very short amount of time. Okay, when they charge up and when they discharge, it takes place in a very short amount of time, in a few seconds only. Okay, and then you look at the part below here. Now, when you hear your teacher teaching you capacitor, or even when you read your questions inside your exam, you will often hear across the term where they say that the capacitor is storing charge. Okay, that's what a lot of people always say. Your teachers will say so, your exam questions will say so. But if the exam question specifically asks you whether does a capacitor store charge, you actually should not say that. Okay, because a capacitor doesn't actually store charge. The reason why we say it doesn't actually store charge is because there's no net accumulation of charge across your capacitor. So if you look at this capacitor here, when it was originally fully charged, you have a charge of negative Q on the right plate, and you have a charge of positive Q on the positive plate. But if you were to consider the capacitor as a whole, your net charge is really just positive Q plus with negative Q, giving you 0. Okay, so there's actually no net charge here. All right, that's the reason why we say your capacitor isn't really storing charge. If you are storing charge, you should have a net increase in charge. Okay, so maybe it's better if I draw another diagram here just to illustrate it to you. You see, in the first place, your capacitor was like this. Let me just try and draw it nicely. This one was your capacitor when it was uncharged, or in other words, neutral. So this plate here had no charge, and then this plate here had no charge. So when we ask you what is your net charge, it's really just 0. Okay, but what happens when you start to fully charge your capacitor? So when you fully charge your capacitor, just now as I mentioned, one plate will become positive Q, one plate will become negative Q. So in your case, you actually had negative Q here and then positive Q here. But when you're looking at the net charge now, considering across the whole capacitor, your net charge, again, really is 0. So you see, from here to here, there's no net change or accumulation of charge. That's why we cannot just simply say that your capacitor is storing charge. If you're just talking about one plate itself, yes, it is storing charge on one plate. But as a whole, across the whole capacitor, it is actually not storing charge. Okay? But what you could say instead is that your capacitor is actually separating charge. If you look at the first page, the first line I mentioned to you, capacitors separates charge, stores energy, or smoothens and rectifies AC. So the part where we say that charge is separated is actually referring to this. You see, before this, if you look at this plate and this plate, there's no charge whatsoever on them, right? But now, after you have fully charged your capacitor, this one consider it as fully charged, you now have negative, 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 negative here, positive, 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 positive here. So you now have charges on your plate, but they are separated. One side is negative, one side is positive. This is actually what we mean by charge separation. Okay, so maybe I should kind of draw it out for you. Just let me go and write something here. This one here, you can say is your charge separation. Okay, you can see that once you have fully charged your capacitor, you notice there's charge separation. Positive is on one side, negative is on one side. So if you are asked about what does a capacitor do, it is correct to say that it is separating charge. Okay, because here electrons are deposited on one plate, while the same number of electrons are pushed off the other plate. Okay, and the same, and then when you think a bit further about this process, because you're pushing and repelling the same amount of charge, you actually have no net change in charge. Okay, so this kind of also kind of explains to you why you do not store charge in the first place. Okay, now the process of you trying to separate the charges actually involves you doing work to move the electrons. So when you do work, you will cause energy change. Okay, so when you were trying to charge this capacitor, what you did was that you tried to push electrons in this direction towards the right plate, and then electrons away in the same direction of the other plate, right? So you trying to push your electrons onto the right plate and then off the left plate involves work. So that work that you do is actually stored as energy inside your capacitor. So this is how your capacitor actually stores energy. Okay, so this is how a capacitor works. All right. So then you move on to the next page. When you're talking about capacitor, there's a quantity called capacitance. There's always affixed to your capacitor. So what is capacitance C here? Capacitance C is actually the charge stored per unit PD applied across your capacitor. This is actually a general definition of capacitance. But if you are asked to define capacitance of a parallel plate capacitor, your definition will need to be a bit more specific, where you say that it is actually the charge stored on either plate of a capacitor per unit PD applied across the plates of your capacitor. Okay, so from the way your capacitance is defined, if you try to work it out in an equation, it's actually C equals to Q over V, where Q is the charge stored and V is the PD across your plates. Now, your capacitance has unit of coulomb per volt, or it has a special unit called farad. Okay, now capacitance is a measure of how much charge can be stored for every 1 volt that you apply across your capacitor. The bigger your capacitance, the more charge it can store. Or in other words, the more energy it can store. Okay, so when you're talking about the charge stored by your capacitor, this one, if you want to make more sense of it, because just like I told you, your capacitor doesn't store charge, right? So if you notice that when your questions always say your capacitor stores charge, for the case of a parallel plate capacitor, it often refers to the magnitude of your charge stored on one plate of your capacitor alone. Okay, so when your question always say capacitor is storing charge, or your teacher always say a capacitor is storing charge, it's really referring to the charge stored on one plate itself. Okay, and then later on you will learn that for spherical conductor, it also has capacitance. So in this case here, your charge stored is actually the charge on the surface of the conductor itself. Okay, right? So this one, just bear that in mind. And another thing that I just need to mention to you is that capacitance value is fixed for a given capacitor, but the PD and the charge stored across it can vary. This is similar to the fixed resistance of a resistor, so PD and current through it can vary. Okay, what do I mean by that? You can try and look at this diagram here. Let's just say I tell you you have a fixed resistor here, and then you have a variable resistor here. I tell you that your variable resistor has a resistance between 1 to 10,000 ohm. And then this fixed resistor that you have here, its resistance is 100 ohm. Okay, so what you do know from your circuit here is that there will be a PD across this fixed resistor here, and at the same time there will also be some sort of current through this fixed resistor here. Okay, so the thing here is this: if your variable resistance, this one is your variable resistance, if your RV is changed, the PD and current through your fixed resistor changes. Isn't it? This one here is your fixed resistor. Okay, it's a fixed resistor. So looking at this circuit here, if you were to change your variable resistance, you can imagine from what you've learned from your DC circuits a few months back, your current will change, your PD will also change when it comes to your fixed resistor here, right? But the resistance of your fixed resistor itself will not change, okay? So that's why here, this is what I mentioned. RV is changed, the PD and current through fixed resistor changes, but the resistance of the fixed resistor doesn't, okay? But the resistance of the fixed resistor doesn't, okay? So this, if you can understand this, you should be able to understand a similar thing is actually happening for your capacitor. So the thing here is this: if say in my case, I have a capacitor that is again connected to some sort of variable resistor, this one here would have this capacitor here will have a certain capacitance value, and it also has a PD across it, as well as a current that tries to flow across your capacitor. So the thing here is that if I were to change the fixed resistance here, if I were to change the variable resistance here, it will actually affect my PD and it will affect my current on the capacitor itself, but it will not affect my capacitance value. The capacitance value will remain fixed, just like the case of my resistance here. Okay, that's what this statement is actually trying to explain to you. Okay, so far so good. All right. Now, when you're talking about capacitance and you want to try to increase its capacity to store charge, you could do a number of things. Either you increase the area A of your capacitors so that more charge can accumulate on the plate, or either you decrease the separation D between your plates so that more charges can be repelled off the other plate, which means to say you have more charge separation. Okay, so this one is just something like general knowledge for you, but it's not in your syllabus. Okay, so if you don't want to remember this, it's fine. Okay, so it's not tested. Okay, now for your capacitor, just now I mentioned earlier in the lesson that your capacitor looks like some sort of cylinder with two legs, right? So for your capacitor that looks like a cylinder with two legs, it's actually still your parallel plate capacitor. It's just that you kind of roll them into a cylinder. It's like you take a piece of paper and then you roll it out, it becomes a cylinder, right? It's a similar concept here. For a parallel plate capacitor, is actually flat in the first place, but you go and roll it out, it becomes a cylinder. So it becomes this in the end. All right. So for the capacitor, usually there will be some sort of markings on your capacitor. All right. So if they tell you the capacitance, say in your case as 4,700 microfarads, this tells you that you have 4,700 microcoulombs of charge that is stored on either plate of your capacitor when the PD of 1 volt is applied across it. Okay, and then after that, you also notice that you have a voltage rating here. This voltage rating isn't talking about the average voltage or the minimum voltage that should be applied to a capacitor, but rather is actually the maximum voltage that you can apply to your capacitor before your dielectric layer breaks down and ceases to be an insulator. Okay, so you want to use this capacitor, just make sure that your voltage is below 25 volts. Okay, so at below 25 volts, every 1 volt you apply would still store a charge of 4,700 microcoulombs on one plate of the capacitor itself. But the moment you apply more than 25 volts, it is no longer a capacitor. It will be damaged and be unable to store charge. Okay, so this is the basics of your capacitor. Right, so with that done, let me just go on to the next page. Now, when you were doing your AS last time and you were learning resistors, you learned how to derive the expression for resistors in series and resistors in parallel, right? You will have to do the same thing here for A2 when it comes to capacitors. So you need to know how to derive the expressions for total capacitance when capacitors are in parallel or series. So the first one that you will consider is this one. Okay, so the first one you'll consider is capacitors in parallel. Okay, so now consider 3 capacitors that are connected in parallel to a supply voltage V, which provides you a total charge Q to your circuit. Now, because this is a parallel circuit, you know that current tends to split across a junction. This also would mean that any charge that you push across the circuit will tend to split out at the junction too. So you imagine right now, this supply voltage is trying to push a charge of Q. But then after that, it encounters this junction here. Okay, now current and charge are closely related because current is rate of flow of charge, right? Where I is proportional to Q here. So you can actually just think of it as this. When current flows, charge must be flowing too. You have more current, you also have more charge. When your current splits up, your charge will also split up. Okay, so here you can imagine that charge is actually being pushed through your circuit, but it encounters this junction here. So from Kirchhoff's first law, you know that current will split up. Likewise, this will also mean that your charges will split up. So this one here will probably cause you to have a charge of Q1, Q2, and then Q3. Okay. And then the next thing to note is what happens when you try to apply Kirchhoff's second law here. For Kirchhoff's second law, we told you that for each branch of a parallel circuit, the PD would always be the same through all the components. So in your case now, the PD across each capacitor is actually the same as your supply voltage. So what do we mean by that is, if you again recall what you learned in your AS DC circuits, let's just say I have a parallel connection that looks like this. Each branch has a different number of resistor. If I were to tell you that your PD across your cell is 12 volts, what you would say is that the total PD across this first branch here will be 12 volts, across the second branch here will be 12 volts, and across the third branch will also be 12 volts. Because when you apply Kirchhoff's second law, for each closed loop, sum of EMF should be equals to sum of PD, okay? So you apply Kirchhoff's second law for each of these subsequent loops that I highlight here, your sum of EMF must be equals to your sum of PD, okay? So now when you look at your current circuit here, by right, your capacitors should all have their own PD. This one could be V1, V2, and then V3. But because they're connected in parallel like this, if you try to consider each loop, V1 will be equals to V, V2 will be equals to V, and then V3 will also be equals to V itself. Okay, so they all have the same PD right now. So with this in mind, if you now want to derive it, you probably will start with something like this. Your total charge is equals to charge at capacitor 1 plus charge at capacitor 2 plus charge at capacitor 3. And then you want to change it in such a way that it has capacitance inside. So you remember capacitance is charge stored per unit PD. So charge here is actually the product of capacitance times PD. So you're going to get this. All right. And also, as I mentioned just now, because of Kirchhoff's second law, the PD across each of your capacitor will be equal to your supply voltage itself. You finally get this, such that the V will cancel off, giving you this final expression here. So you see, this one is your total capacitance when your capacitors are connected in parallel. It is akin to the expression for resistors in series. Notice it's the other way around. If it's capacitor in parallel, you add it like you would resistors in series. Okay. And one last thing to note here is that your charges stored on your capacitors that are connected in parallel will always be in the same ratio as your capacitances because Q is equals to CV. Okay, so Q1, Q2 to Q3 will be equals to C1 to C2 to C3 because here the relation is that they are directly proportional to each other. Okay, so this is for capacitors in parallel. Okay, then you move on to capacitors in series. Okay, now for capacitors in series, you consider three capacitors connected in series to a supply voltage V, which provides you a total charge Q to your circuit. So in your series circuit, PD is shared between all components in the circuit according to Kirchhoff's second law. All right, so here your total PD will actually be divided between your three capacitors, giving you V1, V2, V3 here. Okay, so if you were to try to write out one expression, P is equals to V1 plus V2 plus V3. And then after that, you want to change it so that it has capacitance inside. So C is Q over V, B is thus Q over C. So you put it in, you're going to get this expression here. Okay. And then next thing to note is what happens to your charge. In your case, because this is connected in series, whatever current or whatever charge that comes out of your supply, it will be the same charge through your capacitor. Because you can imagine that it's the same current flowing through your capacitor, it will be the same charge stored on your capacitor too. Okay? So that's what this statement here is trying to explain to you. The current is the same through all components in a series circuit, so your charge Q is the same through each capacitor, and it tends to cancel out. Okay, what do we mean by cancelling out here is something like this. This one, let me just erase this. Oh, this one, just now I wrote here I, right? But this I is actually wrong direction because this is negative terminal. I should be here actually, but in any case, never mind. What you just want to consider here is the flow of your electrons, your negative charge. If you consider a charge of negative Q flowing out, this negative Q will hit the right plate of C1 first. So it get deposited here, causing this plate to acquire a charge of negative Q. And then at the same time, the same charge of negative Q will be repelled off the other plate, causing this other plate here to acquire a charge of positive Q. Because it lost negative Q, so this plate here must gain a charge of positive Q. Okay, so for the negative Q that you just repel off the plate, it will now go to this second capacitor where it gets deposited on the left plate, causing this plate to acquire a charge of negative Q. And again, the same charge of negative Q is repelled off the other plate, causing this plate to acquire a charge of positive Q. So you can see here that the process by right should repeat itself for your third capacitor, such that what comes out of your third capacitor is just a charge of negative Q that tries to go back to your positive terminal. So now if you're considering the charge that is stored on your capacitor or the charge stored on one plate on your capacitor, this one is really just going to be Q, Q, and Q. Okay, so don't make the mistake of assuming that it is 2Q. Okay, it's just Q. Right. So if you want to really prove that it's just Q, what you could do is that you just connect those three capacitors in series across a lamp, and then you trace the charge that comes out of it. You will notice that only a charge Q flows through the lamp. So what we mean is you consider something like this. If this one is connected to a lamp, and then you say that this one is negative Q, positive Q, negative Q, positive Q. But this one is too small. Let me just try and draw it bigger for you. Like this, like this, like this, and like this. Okay. So here is negative Q, positive Q, negative Q, positive Q, negative Q, positive Q. You take the fully charged capacitors in series and connect it to a lamp. What you'll notice is that only a charge of negative Q, only a charge of Q will flow through your lamp. So here you try to consider that negative Q comes out from here. Okay, it comes out from here, it flows through your lamp. Only a charge of negative Q has actually flowed through your lamp before it goes to the other plate and discharges everything here. Okay, so it's really just Q only. Okay, right. So back to the expression for capacitors in series just now. We did not really finish that derivation. So the charge stored in each of your capacitor just now, Q1, Q2, Q3, as I mentioned, is actually just going to be Q itself. Okay, so that expression from above, you simplify it to this, where all the charges are the same. You eventually notice that the charges cancel off, giving you this final expression. Okay, 1 over C is 1 over C1 plus 1 over C2 plus 1 over C3. So this one is similar to the expression for resistors in parallel, but your capacitor here is connected in series. Okay, so it's the other way around. Okay, so that one is for that. And also, one other thing to note is this. There are a lot of questions later on that you see that ask you to calculate the PD across your capacitors. So in the event you're asked to calculate the PD for capacitors in series, some common thing that students often take over from your AS was this. If you remember your potential divider equation, where we told you that you have R1, R2, and R3, if I were to ask you to find out the PD V1 across resistor R1, you have automatically told me V1 is R1 over R1 plus R2 plus R3 times with your B in, right? This is what you are very used to doing in your AS. But when it comes to your AS and it comes to finding the PD across capacitors in series, you should never ever use your potential divider equation like in this manner here. This is wrong, okay? Because if say this one is something like this, where you say C1, C2, and C3, and you want to now find out the PD V1 across your capacitor C1, this expression here is wrong, okay? Because in your case, capacitance is not directly proportional to PD. It's actually inversely proportional to your PD. You can see from your capacitance equation, C is equals to Q over V. C is inversely proportional to V. All right. Whereas when you wanted to use your potential divider equation for resistors in AS, the relation was V is proportional to R. Because V is equals to IR, I constant, V is proportional to R, right? So you could have used, because your potential divider equation is derived based on this assumption, you see. If you remember, the derivation of potential divider equation is derived based on this assumption. Okay, So you cannot use it for capacitor because that same assumption somehow does not apply because it's an inverse relation here. It's not a direct relation. Okay. So just bear that in mind. And last thing that I need to go through with you is energy of a charge capacitor. So just now I mentioned to you that your capacitor stores charge. Okay. Sorry, not stores charge. Just now I mentioned to you that your capacitor stores energy. It doesn't store charge, but separates charge instead. Okay. So when you're charging a capacitor, I mentioned that your charges are being separated across your capacitor. So when we say charges are being separated across your capacitor, it means that you have positive, 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 negative, negative, negative across your capacitor like this. This is what we mean by charge separation. Okay, so when you charge a capacitor, charges are being separated. And when you try to separate the charges, it's due to you trying to push your electrons in this manner. Because let's just say that this one was your, okay, now maybe I should just switch it around following the diagram that I gave you earlier. So it's not to cause confusion. So this one, when you wanted to charge out your capacitor, just now I mentioned to you, electrons will flow like this and get deposited on this plate, causing it to become negatively charged. And at the same time, the same amount of electrons will be pushed off the other plate, causing this plate to become positively charged. So this is what we mean by your charge separation. Okay, so when you are trying to separate the charges, you do work to separate them. Okay, that work that you do is stored as energy in your capacitor. So why do you say that work is done to separate your charges in the first place? It's because you need to consider this. When you first push your electron here, you probably won't encounter much problem because this plate here was originally neutral. But the problem will arise once you deposited one electron here. Because you deposited one electron here, this plate here becomes negatively charged. If you were to try and deposit another second electron to this plate now, it is harder because this plate is now negatively charged and your electron is negatively charged. There will be some sort of repulsion when your electron tries to go to this plate here. But provided your force is enough, you will be able to push it and deposit it onto the plate itself. Okay, and now if you're considering a third electron that tries to move towards this plate here, it again encounters an even larger repulsion because this time your negative charge is caused by two electrons. You're going to have a larger repulsion here. You're going to have to push it more. You're going to have to do more work. Okay, so this part here, when you try to push more and more electrons to the negative plate, you definitely must do work in order to overcome the electrostatic repulsion. The same argument could also apply for the other plate, for the positive plate. So when you first push your electron here, it was mentioned that you would have another electron that's repelled away and it tries to go back to your positive terminal. So this part here, probably no issue because there isn't any forces that try to oppose your electron motion yet. But the problem will arise when you push your second electron here. You push your second electron here, another second electron will be repelled away. But this time, your plate is already positively charged as a result of the first electron being pushed away in the first place. So your second electron, when it wants to go towards the positive terminal, it will encounter some sort of electrostatic attraction with your positive plate. So you actually need to purposely apply a force to push it away. You actually have to do work to push the electron off. Okay. And when your third electron comes over here, it again causes a third electron to be pushed away on the other plate too. This time, this third electron, when it wants to go away, it encounters an even larger attraction also, because this time you have already lost two electrons. Before this, your plate has become more positively charged. So now you can imagine you again need to do even more work. You again need to push even more. Okay, so you pushing your electrons off your positive plate will actually also cause you to do work Okay, so that work that you all do is going to be stored as your energy in your capacitor. Okay, now if you want to find out the energy stored inside a capacitor, you can actually deduce it from your graph. But what graph do you want to deduce it from? You derive that graph from your equation for capacitance, where C is equal to Q over V. You arrange it such that it's becoming V equals to 1 over CQ. If you compare it with the equation of a straight line, Y equals to mx plus C, you will be able to deduce that it's actually going to give you a straight line graph that passes through the origin. If you were to plot a graph of V against Q, where the gradient now is 1 over C. Okay, now the area under your voltage charge graph actually gives you the work done to charge the capacitor, which in turn will be the energy stored inside your capacitor. So if you're trying to plot a graph of V against Q here, it's going to be a straight line graph through origin. That area under your graph now would be your work done. Okay, that area under your graph here would be your work done. So this area here is actually the area of a triangle. So you imagine that this one is Q and then this one here is V. Your work done, or rather your energy stored, is going to be E equals to half QV. But you can also derive two other expressions from there. This one is by you substituting out your Q and V. Okay, because we know that Q is CV. If you were to try to put it into Q, you will get E is half CV squared. And then at the same time, we also know that B is equals to Q over C. If you try to put it into V, you're going to get this, half Q squared over C. Okay, so this one should be okay. Right, another thing that I should mention before we go and take a short break is this. Now, when you're talking about work done, you'll notice that this Q times V is actually Q times potential difference. Under the electric field chapter that you did before this, you also did use an equation Q times potential difference. You remember that I mentioned to you the change in electric potential energy is charge times potential difference. It somehow seems similar to this, isn't it? Where you see is charge times your potential difference. This equation here is only for isolated charge in an E field. Okay, it's a different thing. Okay, for capacitors, although the form of equation looks the same, just that you add a half there, that one is really just specific for capacitors. You cannot use this equation for capacitors because this equation is really only for isolated charge in an E field. Okay, your change in electric potential energy is also your work done now. Okay, because here I wrote here, your W equals to QV is only used to find work done on isolated charge in electric field. This is only for electric field, whereas half QV is only for capacitor. Okay, so that one should be it. And another last thing to kind of mention to you is this. Now, apart from your charge parallel plates, you also have a spherical conductor that can also have capacitance. Okay, it's not just charge parallel plates that can store charge. A spherical conductor can also store charge. So it also has capacitance. So you will be required to derive the capacitance of a charge sphere as part of your syllabus. If you were to consider a isolated conducting sphere of radius r, which carries a charge q and has a potential of V at its surface. As this one is a spherical conductor, you can assume that is equivalent to a point charge. So your potential at the surface is going to be equals to 1 over 4 pi epsilon naught Q over R. Okay, and from the definition of capacitance where C is equals to Q over V, if you were to sub in V into here and try to simplify it, your capacitance for a charge sphere will be your capacitance for a charge sphere will be 4 pi epsilon naught R. Okay, so this one, the derivation is required. Okay, so that one is for this.